Today, we're going to talk about assignment 3, part 2. This is a interesting assignment. It's, certainly one of the harder ones. It's, in my opinion, the hardest one. The hardest part of any assignment you have to do in this course. The reason why is because it's very theory heavy, right? It's the majority of the time debugging, right, that you spend in this assignment are debugging math errors. They're not really debugging, crashes. Even in part 1, you were dealing with a lot of, crashing and sort of data structure work with the BVH. But the majority of points to be lost really here are math related. And another thing to keep in mind is that don't let perfect be the enemy of good. Include any errors that you know about in your write-up so that we can use that for partial credit. And also, we're going to be looking at your code, so that that can be in your favor or not in your favor. So if you're assuming that, oh, I just got my code to look like the reference result pretty much, then that might not be enough if your code isn't actually following the formulas correctly. But on the other hand, if it doesn't follow the reference solution at all, but you mostly have the correct formulas in spirit, you're going to get the majority of the credit on these sorts of problems. Especially, for example, like task 6, which is really hard to get the little bits 100% correct. So today we're going to go over a lot of the theory that we went over in class, go through some examples of some of the harder topics, math topics, and then give some implementation tips for implementing the rest of your path tracers. Okay, so we did this over the last presentation, but just a quick overview of all the tasks. So task 1 is we started generating camera rays, right? So this is just part 1. Started generating rays that came from the camera. Task 2 was ray tracing, right? So getting ray primitive intersections working. Task 3 was involved accelerating these ray primitive intersections using a bounding volume hierarchy, doing the whole partitioning scheme. It was a little bit of algorithms work, classical algorithms work, a little bit of geometry with surface area heuristic. And the 4th task was a little easier, basically an if statement, hopefully, which was implementing direct lighting, right? Adding adding shadows into the existing direct lighting implementation in Scotty 3D by adding a check to see if that ray was hitting something. Okay. So what are we up to now? So task 5 is implementing a basic version of the rendering equation that we talked about in class via path tracing. Task 6 is supporting non-diffuse materials, so namely a refractive material that has a Fresnel term, so it can both reflect and refract light, and a mirror. And task 7 is supporting environment lighting, right? Image-based environment lighting via a texture. Okay. So, all right. So the first thing I want to talk about in this recitation is sampling. And the math is going to get a little bit dense here. So I highly encourage you all to ask questions. I'm okay if it looks like Twitch chat in the Zoom group chat. That's totally fine. Okay, so just some basic terminology, because I realized that technically we don't have, it's not required that you needed to take a probability course, even though most of you likely have. Probability mass function, right? So we have a random variable x, and the probability mass function says, just as review, hopefully, it's the probability that some discrete random event x big X has value little x, right? So this is between 0 and 1. Probability density function is the continuous variant of this. So it involves a continuous random variable, right? So there are, infinitely many, uncountably many different outcomes. The cumulative distribution function is the probability that a random variable, continuous or discrete, is less than some value, less than or equal to, more precisely, right? So big F of X is how I'm going to write it in these slides, is equal to the probability that, big F of big X of little x is the probability that big X is less than little x, less than or equal to little x. And another thing to keep in mind is that sort of, big F of big X of infinity, right? So that's saying the probability that X is less than infinity, which is always true. That equals 1, right? And that makes sense, right? It's probability that it's less than infinity. So it needs to be kind of well defined in this sense. And for continuous random variables, right? So given the PDF, the probability density function, that's the continuous version, we can get the CDF by just taking the integral, right? So what we're doing here is we're just taking the integral from negative infinity to x. So that gives us the sum of all probabilities of all possible events up to x. And there's a similar idea for a discrete random variable, right? So we add up for all possible values x, little x, up to x prime. We add up the probabilities of all of those events up to and including x. Okay, so that, hopefully you've seen something like this before, but probability density function, cumulative distribution function, we're going to be talking a lot about this stuff. Okay, so here's a quick example. So this function in red is a PDF. So this is defined between 0 and 2. So big X is a continuous random variable between 0 and 2. And this is graphing the probabilities from 0 to 1. So one thing to notice is that so big F of X here is the cumulative density function. So just the integral of little f of big X. Okay, so one thing to notice here, in order to be well formed, we need over the domain, right? So from 0 to 2, we need the integral to be 1, which it is. We also need another thing to notice is that the CDF is monotonically increasing, which makes sense. It's just a sum. Okay. And okay, so let's talk a little bit about this technique that we talked about in class. And I just want to give a sort of more general framework for this. So it's inversion sampling that we're going to talk about. So the general goal of inversion sampling, right, is we are given a PDF, little f of big X of X, for some random variable. And we want to generate this big X, this random variable, such that it follows this just random distribution that is thrown at us. Okay, so how do we do that? So 4 basic steps. So step 1, first we have to find the CDF. So that's usually involves taking the integral, or we might already know it. So we have to, then we invert the CDF to, the technical term for this is the quantile function. And this should satisfy, but it's just the inverse function, right? So Q of X of f of X, where big F of X is the CDF, that should just give us X. Then we generate a random number uniformly from 0 to 1 and just apply the quantile function to the uniform sample, right? So, and then what this is guaranteed, if you can follow these steps, some of these steps might be non-trivial, but if you can do them, then you're actually going to be able to recover the original distribution. Okay, so let's talk about this in the discrete case. That's a little bit abstract. But the way I like to think about this in the discrete case is we can kind of imagine the CDF as sort of stacking blocks, right? So let's say in this case there are four possible events, right? So each event has height equal. Sort of we create a block for each event with height equal to the probability mass function, right? So then what we can do is just stack them on top of each other into like a little skyscraper. And then all we need to do is pick a random height. And so by virtue of our like construction here, we chose heights of the blocks that give them sort of a higher representation, in the height domain. So that if we choose a random height, we're more likely to choose things with a higher probability mass function, which is exactly what we want, right? Like the whole point is to choose something with high probability, right? So that has the probability, the value in the probability mass function that's high. So that's the basic idea, right? So you can think of it very geometrically in this way, especially in the discrete case. And it's really the same story in the continuous case. I mean, you need to think of it a little differently, but if we sort of think about it, I mean, just because of how, I mean, this is just true by virtue of how an integral works. Sort of intuitively, areas with very high probability will increase the slope here of the integral, right? Of the CDF. So it's going to have more space, if we're sort of kind of choosing some small piecewise part of the y coordinates here, we're more likely to choose some small patch if it has a high probability. So it's the same general idea, right? You can think of it as sort of this block idea, but to the limit as the number of events goes to infinity. It's another way to think about it. So yeah, so just like before, it's just we're basically going from sums to integrals. It comes over pretty nicely. Okay, so this is actually this problem is an old exam question that was motivated by a game I actually worked on where I had this problem. I needed to spawn in a whole bunch of enemies in between two concentric circles, right? So this actually didn't start as an exam question. It started as a actual problem I encountered when making a game. And so the problem is, suppose we want to find a function. We have two random numbers, right, a and b, that are generated between 0 and 1. And what we want to find some algorithm, right, that basically mutates a and b into a random point in between two concentric circles that are located at the origin, right? And then these circles have radii r1 and r2. We can assume r1 is less than r2. Okay, so how do we do that? Okay, so one way that, and we'll talk a little bit more about rejection sampling later, but we can use rejection sampling, right? So like we can put a box around it, and then we can, just throw points at it. We can just throw values at it, random values in that region, and then we can just reject the ones that are not in between the two circles. That's one way to do it, but that'll lead to a large amount of rejected samples, especially in this case, right? Because we have this inner circle that we want to basically not count. So really, this is a specific case where inversion sampling is going to be really useful. Okay, so and you'll find this is a kind of common theme whenever we're doing these sort of inversion sampling problems, is coming up with a parameterization. So in this case, we're going to parameterize this circle in polar coordinates. So we are going to start with, we're going to have an angle big theta and big R. So R is just the distance of, so like, let's say this is the point that we want to generate, right? Our random point. Then we're going to say big R is the radius to the, of the point with respect to the origin. And theta is the angle from the horizontal, right? So this little r here is representing the radius, right, of x, y, and then the angle is just the angle from the horizontal. Okay, so circular coordinates, and so we want to find the CDF, right? So what is that? So that is the probability that big R, right? So we're selecting a random point here. So we want to find the probability given any random point, right, in between the two circles, that big R is less than or equal to R, right, which is the actual radius here. Okay. So how do we do that, right? Does anyone have any ideas? Give you a few seconds for this. Right? So one thing you can think about here is sort of each ring, right? So like think about it this way. We have this point here, x, y. What about a point that was right here with the same radius? Is that point as equally as likely to be chosen as x, y? Well, it is, right? Right? Because, it's invariant to the angle that we choose. Sort of we saw this when we were talking about inversion sampling a circle, right? Not two concentric circles, but just a single circle, right? It was only really the probability function only depended on the distance from the origin. So it did not depend on the angle at all, right? We could almost imagine sort of unrolling the circle, cutting it in half and unrolling it, and it would still be fine. It would just be the length of the circumference of the circle. The real tricky part is that if we were to just uniformly sample within the circle, just sort of giving some intuition, if we just let theta be random and r be random uniformly from 0 to 1, we would get a higher concentration of points towards the center of the circle. The reason why is because as we increase the radius, right, the circumference of these circles grows, right? So there are more points as r, and if we consider the circle as r increases, right, as this orange circle grows, right, there are more points on the border as that circle grows. So therefore, we need to account for that. Okay. So, okay, yeah. So do we need to worry about f of theta, f of big theta, right? So again, we're looking for the probability that given a random point in here, right? So this is a function, right? So little r is the input to this function, and we want to know what is the probability that the radius that was chosen, right? The radius that was randomly chosen is less than or equal to this input radius. But do we have to have a similar function for theta, right? So, but we just said no, because the probability that given the same radius, right? If we have 2 points with the same radius, they're just as equally likely. So the probability does not depend at all on the angle here. So we actually don't need to worry about that, and we're going to kind of get at that more rigorously in a second, right? So it's constant with respect to theta. So in this case, the CDF is just the ratio of the areas, right? So all we're doing here is we're comparing the areas of this orange circle with the circle in between R1 and R2. Okay, so we have this sort of larger torus that's spanned by the orange and blue regions. And then we have the smaller one that's spanned just by the orange region. So we're taking the reciprocal of the area of the orange region over the area of the orange and blue regions. And that makes sense, right? Because the probability that it's inside that this random point has radius less than some r is proportional to this ratio of areas, right? Because I hope it's fairly obvious that that's true. That we can just take the ratio of the areas, and then that will translate to the probability that the radius is less than some r, right? When we represent this point in polar coordinates. Anyone have questions about that? Anyone confused at all? Let's see. Okay. Okay, so moving on. So we have our CDF, right? So the ratio of the areas. And the next step is to invert this guy. And then we can generate a random number and we're done. So we've kind of done the hard part, right? The part that requires lots of intuition. We're thinking. So now we can just solve, Q equals big F of big R of R. Right? So the equation that we just found, we just inverted. So we have Q equals the ratio of the areas, and then you do a bunch of algebra, and you get R equals square root of Q R2 squared plus, that should say 1 minus Q, not 1 minus Y. Fix that actually. I was using Y, but we already have a Y. Okay. Okay. Times R1 squared, right? So this actually looks like the equation that we came up with for a circle in lecture, right? Uniformly sampling a circle via inversion sampling. We just sort of have to add in this 1 minus Q term for dealing with the inner circle. So we have our inverse CDF, okay? Just this expression we just evaluated. And, okay, say we have two uniformly random variables, x and y, in the range 0 to 1. So how do we actually generate the final point x and y? Well, first we compute the polar coordinates, right? So we compute big theta and r, so big theta, we had established has a uniform, theta, we're still going to have a uniform distribution around the sphere if we just allow theta to be uniformly distributed between 0 and 2 pi. That's sort of what we were talking about a little bit. It's a little bit more formalized here, that we're still going to achieve a uniform distribution because there are just as many points given a fixed radius, right? There are just as many points along, each of those equivalence classes, you can think of it. The radius, however, is really what we needed to deal with here. So that is why we needed to go through this whole routine of building the CDF, inverting it, generating random number, and applying it to the uniform sample. So, yeah. So those 4 basic steps are pretty solid. Feel free to refer to them. Okay, so we have it in polar coordinates. The last step is just to convert these into normal coordinates, right? So now all we need to do is do the whole r cosine theta, r sine theta to convert from circular coordinates, polar coordinates, to Cartesian coordinates. Okay. Another example. So this one is one that I think a few people were confused about in the lecture. But let's talk a little bit about uniformly sampling the hemisphere. So this is something that, so that last example was a little bit of a warm-up. But uniformly sampling the hemisphere is very applicable to path tracing. We actually give you an implementation of uniform hemisphere sampling, but you guys should absolutely know what is going on, how it can be derived. It's a very important kind of mathematical identity. So given 2 uniform random variables, same situation, we want to generate a point uniformly randomly on the surface of a unit hemisphere. So just like before, the first step is we have to parameterize the hemisphere. So we can do this in 2 variables. And you've probably seen something like this in your calculus class, this parameterization of a hemisphere here. But, just as a sanity check, we should make sure that, summing up the coordinates, And squaring then gives us the radius, right? That's just the definition of a sphere. And to derive this, one way to do it, there's this math stack exchange link that I encourage you to check out if you're a little confused on this. But to derive this, you can just first find z from phi, and then project down onto the plane. And then you can just work in polar coordinates. So meaning, we start with z, right? So z is just cosine theta, right? So we start by getting z from phi. And then when we project downwards, we will use sort of the projected radius downwards multiplied by this theta term, which has to do with sort of how far rotated around the plane it is. So again, the actual derivation is in this link. He explains it fine, and this is probably something you've seen in your calculus class. But let's take for granted that this parameterizes a hemisphere pretty nicely, where phi is defined, by the way, from pi over 2, or 0 to pi over 2, and theta is defined from 0 to 2 pi. So as before, we notice that the PDF is only dependent on phi, right? This latitude term, because there are just as many points in each equivalent longitude. So the next question is, what is the PDF, right? That says so this is actually writing out the CDF here. So sorry about that. Yeah, so this is not exactly this is actually writing out the CDF, so sorry about that. That was an inaccuracy. But we're looking for the PDF here. So really what we want for the PDF is we want what sort of intuitively what you can think about. See, I'll correct that error. But intuitively for the PDF, right, so for little f here, what we want is the integral across all latitudes and longitudes to equal 1. Right? And we want each of these little pieces to have a sort of uniform representation. So one way we can think of it is we can sort of divide up the hemisphere into rings of equal latitude, right, of equal height on the sphere. And so the PDF is just the sort of area, the circumference of each of those rings at the equivalent latitude over the entire surface area of the hemisphere, which is 2 pi. Okay, so there's a little drawing of this here. So here's like a circle given this point with the same latitude. And yeah, so it was sort of what I was saying before. This kind of captures the idea that there are also more points at lower latitudes, right? Which we need to account for. That's the whole problem we're trying to deal with. Because otherwise, if we just naively randomly chose phi and theta, what we would have is we would have more points up here at the top than down at the bottom, because the bottom here is stretched out in relation to the top. So we can't treat these latitudes the same. We can treat the longitudes the same, though, for the exact same reason as the last problem. Okay, so we can actually write this out. So, okay, so what is the piece of the hemisphere at latitude phi? Well, based off of our, so given some phi, right? So we can just write out the size of this circle based on the x and y coordinates. So, 2 pi r is the circumference of a circle. So the radius in this case is square root of x squared plus y squared times 2 pi to get the circumference over the surface area, which is 2 pi, surface area of the hemisphere, which is 2 pi. It's just a fact. So those go away. replace x and y with their actual values, and we see that, as expected, there is no dependence on theta, right? So we've basically just shown that we don't depend on theta for our probability function, right? So that's a more rigorous kind of argument for that. And as a sanity check, if we think about it, right? So if we integrate all possible latitudes here over all possible latitudes from 0 to pi over 2, well, the integral is 1, which is what we want because it's a probability distribution. Okay, so that's a good sign. And okay, so now let's compute the CDF. So that's just the integral. So it's 1 minus cosine phi. The integral from 0 to, this should be, yeah, so this is from 0 to phi. Okay, so now we have the CDF. Then we can get the inverse CDF. So this is a little weird. We have to compute an inverse cosine, which kind of stinks. But, doable. So how do we actually generate the result here? Okay, so we have all these numbers and equations. How do we turn that into an actual algorithm? Okay, so first, going back to those 4 steps that I introduced earlier. So we can pick a random x and y in the range, each in the range 0 to 1. Then we can set our phi, right? This is the altitude, the latitude, equal to this quantile function, right? Evaluated at the random variable. So this is just the inversion method, classic inversion method. And then sort of almost exactly the same as the last example, really. We set theta equal to 2 pi times y, the other variable, because we can uniformly distribute this around. And then we get xyz from the parameterization of the hemisphere, from these guys up here. So we have these values, so we can just compute xyz from our parameterization. So also recall that, x is between 0 and 1 anyway, right? So the inverse CDF is just 1 minus x. 1 minus, a uniformly random variable between 0 and 1 is basically the same as just saying x. The probability of every number is still the same. So we could also just write the quantile function as cosine inverse of x, or cosine of x. And what do you know? So like we give you in Scotty 3D, there's this in sampler.cpp, there's this uniform hemisphere sampler 3D. And I actually wrote this before looking at our implementation. And I actually happened to switch what I called phi and theta, but they came up with the exact same derivation. So this is how they must have derived it. So we generate 2 random numbers. We have an arc cosine term to evaluate the inverse CDF. We get our longitude value, and then we apply our parameterization to recover the actual point. Okay, are there any questions about this? This is highly relevant, especially if you want to implement cosine-weighted sampling, because you're going to need to know the PDF in order to do that. Okay, no questions. Yeah, this is a little bit of a difficult topic. So yeah, I'll also be fielding questions on Piazza and whatnot about this, because yeah, especially for people who haven't taken a probability course yet, this can be a little challenging. Okay, so I want to talk a little bit now. I'm jumping around the tasks because task 7 is totally different from tasks 5 and 6. So task 7, in that task, you're going to be implementing a new type of light. So it's an environment light. So in this task, this is referring honestly to a generally very useful and common technique in CG called image-based lighting. You see this all the time, even in games outside of path tracing. You see it all the time uh, inside of path tracing, right? So it's very common, for example, in a game to have a sort of skybox texture that illuminates an environment. So you're creating an approximation of what you guys are going to be implementing here. And it's, of course, also ubiquitous in movies, right? Because then we can just take a picture of objects that are into distance, and then they can light our scene. And so, broadly, this allows us to take a high-resolution 360-degree image and use it as a light, right? To capture the radiance in each direction, and then use it as a directional light, sort of from all directions. It's a very useful tool. And you can notice that, look at the parameterization here. This is almost exactly the same as the previous example, except, of course, we're not talking about a hemisphere, we're talking about a sphere now. So we're working pretty much in this very, very similar math here. So for part one, you're going to need to do some basic calculations of uniformly sampling a sphere, not a hemisphere. But a lot of the ideas are pretty much exactly the same. So for part two of task 7, though, we're going to need to use inversion sampling to implement importance sampling. So the basic idea here is we want to generate samples of this environment map that tend to be in areas of the image, right? Areas of the environment map that are of higher intensity, right? So we would want to generate more samples, presumably around the middle of the image and around the top of the image of the sky, which would have a higher radiance than the rest of the scene. So again, broadly, areas in the environment light with higher radiance should be sampled more often. So think back again to this image, this analogy of building up blocks and picking up random height. So what we're doing here is we're building up a massive probability mass function, right? Where the number of possible events is choosing each individual pixel. And the probability of sampling that pixel is proportional to the radiance at that pixel, right? So again, you can think of it as a block, right? This block analogy, we create a stack of blocks. The height of there's one block per pixel, and the height of each block is the radiance of that pixel. And so all we're doing is we're choosing a random height. So pixels with higher radiance will have a higher probability of being chosen. So there are some notes that we give you on how to figure this out, how to actually go ahead and implement this. The real challenge is that it's scalability. You need a pretty efficient data structure to compute the CDF, without wasting memory or whatever, doing too many copies. So that's really the challenge. But I think we give plenty of notes. But the general idea is to build up a discrete CDF like this. Okay, so that's all I'm going to say about sampling. Does anyone have any other questions about sampling? Any of the examples we talked about? Let's see. We're doing good on time. Oh yeah, we're doing pretty good on time. Okay, good. So let's talk about Monte Carlo. So probably, especially those of you who are computer scientists, here's a characterization of a Monte Carlo algorithm that you're probably most familiar with from earlier courses. Right? And it's an algorithmic perspective, right? So we have this idea that a Monte Carlo algorithm is a non-deterministic algorithm that, for any input, gives the wrong answer with some probability, and also has a deterministic worst case running time. So this really has nothing to do with sampling or probabilities or that kind of thing, the types of Monte Carlo algorithms that we talk about in this class, but it's a very related idea. In particular, this epsilon here, the larger the epsilon, the more noise we have. So, we'll see this, right? So even though we don't really think about Monte Carlo algorithms in the sense that you would find in, for example, 15251. This is from 251. It's still the same thing, right? So you can keep that in mind in the back of your head, especially if you have lots of experience thinking about Monte Carlo algorithms in this way. And the main takeaway of this is that what we're gambling with, right, is correctness and not running time, right? So, these algorithms, there's a few different fun little names for them. This particular one is named after the Grand Casino Monte Carlo. Everyone just, when they talk about this, shows like the one picture on Wikipedia of Monte Carlo, but nobody actually shows the casino. This is the casino. But you can contrast this, right, with a Las Vegas algorithm, which instead gambles with running time and not correctness. So you know it's going to be correct, but you don't know how long it's going to take. Okay, so that's, a Monte Carlo algorithm. What are we talking about when we are referring to Monte Carlo integration? So it's sort of this class of Monte Carlo algorithms that aim to evaluate a big integral. So from an algorithm's perspective, one way you can think of it is it's a non-deterministic analog, a Monte Carlo analog to Riemann sums, right? So we talked about this a little bit in lecture. So a Riemann sum is just sort of a uniform sample of different points along some integral, and just using sort of the trapezoid rule or higher dimensional version of that to actually integrate the thing. But you can think of it, if you're in that algorithms mindset, it's sort of the dual problem, non-deterministic version of a Riemann sum. So from a statistical perspective, though, what we want to do, excuse me. So from a statistical perspective, though, right? You can look at it. We can think we're setting up a random event, right? Such that we want to control the expected value of that event, such that it's the same as the integral that we're trying to evaluate. Something that we mentioned in class and is very important when we're talking about Monte Carlo algorithms, Monte Carlo integration, is the law of large numbers. This is actually the crucial thing that allows it to work. And it says that when we are taking a very, very large number of samples of some probability distribution, the average approaches the expected value as the number of samples goes to infinity. It really, how quickly it approaches the expected value, it remains to be seen. And we can apply techniques of variance reduction to make it approach the expected value a little faster. But in general, this is really the tool that we're using, is the law of large numbers. And you can see it, right? So like in these images below, you can see as we increase the number of samples per pixel, as we increase the number of samples, you can see that there's less and less noise, and it approaches sort of that Platonic ideal of the Cornell box that we would want. So, okay, let's get a little bit more concrete. And this is sort of the classical example of Monte Carlo, of a Monte Carlo algorithm that you would find, like online or in the wild. Computing pi. Okay, so how might we compute pi, right? So we want to compute pi using a Monte Carlo algorithm. I think I kind of gave it away earlier. But so, if the area of a circle, right, is pi r squared. So if we can find the area of a circle with radius 1, okay, then we've found pi. So we'll use rejection sampling, right? So we can try that. So, we can draw a circle on the ground with radius 1, right? We can put a box around it and, throw some rocks at it randomly, uniformly sample the box. Importantly, we're uniformly sampling a box, right? So we don't need to know pi to do this. And that's the whole point. We don't know pi, we want to find pi. And okay, this is a little weird. So it turns out that the quantity 4 times the number of samples in the circle over the number of total samples is equal to pi. Right? So the number of samples in the circle over the ratio of the number of samples in the circle over the number of samples in the box times 4 is equal to pi. Where did that 4 come from? It's a little weird. I mean, you can kind of think about it like the number of samples in the circle over the number of samples in the box. That's pretty high, right? So, it's a pretty high fraction. And we're multiplying it by 4, and pi is approximately 3.14, so that kind of makes sense intuitively, right? It's going to be kind of close to 3.14, but how do we get how do we know it's 4 exactly? Like, is 4 some magical number? Well, okay, what are we doing here? Like, step back a little bit. And there's this beautiful tool. I actually didn't really know the name for this, and I guess I'm proving the name of it right until I was writing this lecture. But it's called the law of the unconscious statistician, and it is called that because apparently it is called that. It's sort of an inside joke between statisticians that that students tend to use this without realizing it. And you'll see what I mean in a second. So here it is. So the basic idea is, I have the discrete version written down, but we're mostly going to talk about the continuous version. So we have a random variable x and a deterministic function f. And the idea is that the expected value, right? We're trying to find the expected value of f of x. Okay, and what it is the integral over all x, right, of the value f of x times the probability that this variable x equals x, right? So the really powerful thing about this is we can find the expected value of f of x, right? So we're trying to find a value of a function, the expected value of a function called on x, without knowing the probability distribution of f, right? Or sorry, of f of x. We only need to know the probability distribution of x itself. That's a very powerful concept. I mean, it underpins all of Monte Carlo algorithms. So that means we can, choose this random variable however we want, and we can choose any function f, and then this will always work. And so we're going to see this coming back again and again, especially as we kind of start to bend probability distributions, especially considering variance reduction. Okay, so let's apply this to what we've just been doing. So for computing pi, we have x, which is our variable x, which is a random point in a box. And in this case, it's pretty simple. Our f of x is just 1 if x is in the circle and 0 otherwise. So x is in the domain of the box, not the circle, so it can be 0. And the probability function, right? So what we want is over the entire domain of all events that we're talking about. We want the integral of all of that to be equal to 1, right? Because it's a probability distribution. And it's a uniform probability distribution in this case. So it's just 1 over the area of the box, which is 1 over 4. It's like, okay, that's where the area comes from. That's where the 4 comes from, rather. Okay, so let's just, plug and chug. We have the expected value of f of x equals the integral over the box of f of x over the area of the box. So that's just 1/4 of the area of the circle. Well, the area of the circle is pi, right? So the expected value of our function f of x is pi over 4. Well, great. Now all we need to do is remember the law of large numbers, and we're basically done, right? So the law of large numbers told us that the expected value of the number of samples inside the circle over the total number of samples approaches the expected value. So that quantity approaches the expected value of f of x as the number of samples goes to infinity, right? So really, we kind of have these two fundamentally important ideas. We have the law of the unconscious statistician, which is how we can compute the expected value of something while only knowing the probability distribution of its input, and the law of large numbers, which says that if we just throw a ton of samples at something, we can approach its expected value. Okay, and that's generally true. And you can imagine that right now this is a very simple function f of x, but as we, move into the rendering equation, f of x, of course, is going to become quite complicated. But we're still going to keep in mind these fundamental principles. So, okay, I would imagine that for a lot of you, you are looking at this and just kind of freaking out, and that's okay. Like, oh my gosh, like I totally forgot all of my Calc 3D, or I totally forgot all of my probability, or I haven't done probability since concepts, and that is totally fine. I sympathize with you. I was probably in that position when I took this class. So what I would recommend you check out is these tutorials by Scratch a Pixel. So I have some links here. If all of this totally flew over your head, read this Mathematical Foundations of Monte Carlo Methods. This goes over all of the probability theory that you need to know. And also, if you're motivated, also go ahead and read Monte Carlo Methods in Practice, which goes into other applications of Monte Carlo methods to rendering. It goes beyond Monte Carlo integration and also talks about Monte Carlo simulation, right? So for simulating like little particles, for example, you can use Monte Carlo methods. It's a very interesting read. Honestly, for me as well, I got a lot out of it reading it, preparing for this lecture. So I highly recommend you take a look at this. Okay. So any questions about that? Any questions about Monte Carlo? Okay. So now we're going to get a little bit more specific about this assignment. I would assume some of you guys have kind of been waiting for that, but that's okay. I had to get through the dense theory stuff first. So let's talk about the rendering equation, specifically how we do that in Scotty 3D, how we actually implement the rendering equation. Okay, so here it is. So this is the formulation we gave in lecture. Big rendering equation. Now, one thing to keep in mind, by the way, is you should know all of these terms, just in general. It's a very useful thing in computer graphics, just as a graphics engineer, to know all these terms, where they come from. And also, from a more practical perspective, we have had a question on an exam more than once that was, on the final, that was just giving you the rendering equation and telling you to label it. We've had that, so it behooves you to just learn this. One, for this assignment, and also just in general. So, okay, so diving in a little bit. So right now we're just going to talk about three of these terms. So LO is the output radiance. So radiance is the amount of energy per unit area per unit solid angle, right? And so we have output radiance and incoming radiance, and that's why, again, this is a recursive function. That's why light needs to bounce off of different objects. And then we have the BRDF, right? The bidirectional reflectance distribution function, which is a probability distribution, right? So you should be thinking echoes of the law of the unconscious statistician here, right? We're multiplying by a probability distribution. Okay, so broadly, your task is to implement a Monte Carlo estimator for the rendering equation, right? So, okay, how do we do that? So absolute basics, right? So your inputs are WO, right? The outgoing radiance, and P, which is the point of intersection, right? So, the outgoing ray direction, rather, and P, which is the point of intersection, right? So we just raycast into the scene with some bundle of light, and the confusing thing, right? The thing that especially gets newcomers who are just looking at the code is, okay, remember, I mentioned this in the part 1 recitation, that the rays are starting from the camera, right? In fact, you implemented this in part 1, right? When the algorithm starts, the rays are going to come out from the camera, which obviously isn't what happens in real life. In real life, light comes out of a light. It does not come out of your eyes. So it's a little bit backwards. So wait a minute. How can we even do that? Right? Like, rays don't start at the light; they start at the camera. So how can we even do that? How is this even possible? Well, there is this physical property. I don't remember if we talked about it in lecture yet. We definitely will at one point, called Helmholtz reciprocity. So it basically means that the BRDF is reciprocal, right? So the probability that from some direction, incoming direction WI, that we go out into direction WO is equal to the other direction, right? If we turned the scene around so that our incoming direction was WO, it's the same probability that it'll go out to WI. This is true for most surfaces that you find in nature. And broadly, I mean, this means that if you have, your eyes and a camera, right, and some lights, and you all rotate, simultaneously, you're going to see the same image, right? So like the angle that you actually look at an object is not going to affect the color that it is. But is this a universal quantity, right? Is this a just total truth? Well, no. And I invite you to think about different surfaces that do not obey this reciprocity. But my favorite one are these guys. I remember Pokemon cards that were like this when I was a kid. These lenticular prints, right? So the idea is, I mean, these are almost a canonical counterexample to reciprocity, right? So depending on how you look at this thing, it's going to look different. Yeah, Mark, you raised your hand.
Yeah, so I just had a question. So should the WI point into the plane, uh, or isn't it the incoming direction? It's pointing like away from the plane.
Yeah, that's a great question. So technically, yes, it should point into the plane. It's honestly a question of your coordinate basis. I'm going to talk a little bit about specifically to Scotty 3D in a moment, but in specifically referring to Scotty 3D, actually all of these rays are leaving the surface. So it really is a question of your coordinate basis, right? Like you can imagine in your BRDF, right? Your BRDF needs to be actually written out at one point. You can just invert WI and you get the same expression, if that makes sense.
So is that what you mean by the Helmholtz reciprocity? You can just invert WI?
No, that is not what I mean by reciprocity. So reciprocity means, maybe I can draw a little thing here. So let's say I have a surface, right? And we have a camera here, and then we have here's our object, and we have a light here, right? The color of this object, right, will be the same if we switch these. Right, okay. So the color that this camera observes to this object will be the same if we switch these, if the BRDF of the surface obeys reciprocity. That is
Oh,
not true for this, right? For this example down here, the lenticular print, right? You can tell, like, right, like just by definition, by moving your perspective around the object, even with the same lighting, even with the same, all of the same sort of scene characteristics, if you just change the angle that you're looking at the object, it's going to look different, right? Another example is like the back of a CD. That's another canonical example. And something you'll actually find that's pretty common between all of these objects is that they have some sort of microstructure that basically has like little tiny billboards that are facing in some direction. So like with a CD, you have these like little digital holes in them, like little imprints. And in these lenticular prints, they're just very, very finely kind of configured so that they have this like weird property. But so, back to your question, reciprocity has nothing to do with just our canonical basis for WI and WO, right? Like, let's say our BRDF was, so we chose like a, purely retroreflective BRDF, right? So retroreflective means it just goes back in the direction that the light came from, right? So let's say that it was just, our BRDF was F P W I W O. So here we could write it like if it's, retroreflective again. And usually a retroreflective surface would look something like this. So let's say here's the incoming ray direction. It would look kind of like that, right? It would have like a little bit of an oval, but going back in the direction. But I'm saying, let's just be even more simplistic than that and just say that when a ray of light comes into the surface, it just goes straight back, which doesn't really happen in real life. It's pretty rare for that to happen. But let's just, for the sake of example, say that. So, we'll say that this is like some alpha. I'm going to ignore the you probably need to divide by a cosine theta for this to integrate, right? But I'll just say some alpha if Wi equals Wo and then 0 otherwise. So, if we're talking in terms of, okay, Wi and Wo are both have, a positive Z value, right? Or, they're both going away from P, then this is right. But if you wanted to define this coordinate plane such that we had these two, right? It's like, okay, sure, then we can just add a minus sign here, and it's still correct. That's all I'm saying. Right? It's like when we're defining the BRDF, we just need to be consistent in our coordinate bases, right? Like the way that I'm defining it here, this is a retroreflective surface, right? Because then Wi and Wo would be in the same direction. An orange line and this black line would be in the same direction. In this case here, it's just I just need to stick a minus sign, and then it's correct. Does that answer your question?
okay. Yeah, that makes sense. So in this diagram that you drew here, this WIW or the orange rays, where would the camera and where would the light be?
So we don't really know that, right? It's actually irrespective of the camera and the light, because recall that, like, I mean, the whole point of what we're trying to do here is we want, let's say we have a light here, and our camera is here. We want to be able to, do something like this and eventually hit our light, right? So this could be on this bounce, it could be on this bounce. We really don't care where the camera came from. What I will say is that these still are defining this WO is the excident direction, right? The direction that the outgoing direction, right? So if we're thinking about this in terms of like photons, this is the direction sort of towards the light, and this is the direction sort of towards the camera, right? So
Okay.
so this direction here is WO, right? And then we have WO. Wait, no, I got that backwards. Wait, did I? Wait, yeah, no, never mind. Yeah, so this is WO, this is WI.
Oh, okay. I see. Okay, I get that.
Okay, and and the key idea of reciprocity, right, is it says that we can, if we want, we can have WO be given, right? So in this case, WO is given, right? We know WO, right? We know the direction that the photon is traveling in, but we can flip it because we can say, okay, we're going to start at the camera now, and we're going to see it when we want to hit, when we hit a light. We're going to try and bounce around the scene until we hit a light, instead of starting at the light, bouncing photons around the scene until it hits the camera. And the reason
Yeah.
why we do that is because if we didn't do it that way, there would be, millions of photons, far more, that, would just bounce off into random directions and not hit the camera. And there would be so much wasted space. Whereas if we start at the camera, we know that, it is far more likely that we're going to actually get some signal, right? And that we're actually going to hit a light. So that's why we want to do that. And it is sort of a really nice kind of coincidence, physical coincidence, that we have reciprocity, and that most surfaces behave like. Does that make sense?
Makes sense. Yeah, that
Yeah.
makes sense.
Yeah. So that was a great question. I mean, it's a common point of confusion, this assignment, because it's really easy to fall in that mindset of, oh, a ray is a photon or a small bundle of photons. But really, that's a useful mental model, but it's not a complete mental model, because really what we're dealing with here are kind of like light paths to a light. And once we find a light path, we need to kind of have this, we need to keep in mind the accumulated sort of radiance of all of the surfaces we've hit. Right?
Makes sense.
Yeah. So in each of the incoming directions. So yeah, great question.
Yeah.
All right, any other questions before I move on? Well, I'm still talking plenty about the rendering equation, so. Okay. I'm gonna mute you, Mark.
Yeah.
Okay, so next thing I want to talk about is direct lighting. So this was in task 4, right? We talked about this idea of being directly lit, and you guys implemented a shadow query. And kind of what you guys did is you just kind of like ignored the actual shadows, or sorry, the actual rendering equation part of it, because we didn't cover it yet in class. But it is worth going back and trying to understand how exactly direct lighting fits in to the rendering equation. And so, something I've seen some students conjecture is that the direct lighting term is in LE here. It's not. The direct lighting is still part of the inside of the rendering equation. And Keenan specifically actually talked a lot about like the general technique. So one way to look at this is, we know that for each light, right? So we're defining a light as sort of a separate thing to a surface, right? So a light in Scotty 3D, the way we're defining it is sort of like, it can only emit light. It can't like bounce light and emit light at the same time, right? It's just a light. It just has a constant irradiance, right? Or a constant radiance in all directions. Okay, so one way to think about this is we could only sample all possible WIs, all possible incoming light directions that hit the light, right? So we can take the little section of our hemisphere, right, that hits the light, and only integrate over that. Alternatively, and you can see that in this, I recommend you go back to lecture and see Keenan's explanation of it to get a better feel for how this integration actually happens. But the basic idea here is, instead of integrating over this little region of the hemisphere, hello, on Zoom, all right, we're instead going to integrate over this region. We're going to integrate over the light surface itself. Okay? And basically what we're doing is we're adding in this term here that projects the area of the light onto the hemisphere. So that's what's going on here. That's what I'm trying to show here. So we're integrating over, right? Our integral is defined, the domain of the integral is over the surface of the light. And what we're doing is we're projecting each small, area, each dA prime, onto the hemisphere. And so this change of variables needs this sort of normalization term. And so, yeah, that's really what's going on here. And, oops, sorry, I skipped ahead. Clear all that. And so, yeah, in task 4, you kind of just tacked on the shadows. Kind of just like said, okay, here's an if statement, because I don't know what this is doing yet. And that's fine, but really, concretely, in terms of this, you added in this V term, right? This is true if the if P prime, right, if this point on the area on the light is visible from the point on the surface, right? If it's occluded or not. That's what you implemented. So yeah. So again, the general idea is integrate over the light's surface, and you have to account for the change of variables, these sort of change of terms in the integral, to talk about the domain being over the actual light. Something else that I want to talk about is there's actually another way to emit light in Scotty 3D that, in fact, none of the actual examples that we give you use this, but it's still possible. It's still something I kind of wanted to talk about because, at the very least, people are a little bit confused about this term in the rendering equation. So another way to think about lights is that they're just normal surfaces with this term LE, the emitted radiance. So what this means is that this is non-zero when the surface itself is a light. So here for this surface, right? Okay, let's think of these terms here. So we're starting at point P. So at point P and going in some direction WO, right? The emitted radiance is 0. Okay. But we may have, right, recursively, we could evaluate the rendering equation, shoot out a WI, right? So in this term, shoot out a WI, hit an emissive surface. And this emissive surface, right, so starting at P prime and going in direction WI, right, or negative WI, really, because we have to account for the change of bases here. This is going to be greater than 0, right? So this surface is emitting light. So I've also drawn this surface like with a little bit of these brown spots because the main advantage, right, you might think, well, the whole reason why we did this change of bases stuff is so that we didn't have to do a direct integration, right, a uniform sampling of the entire scene. We didn't want to do that, right? All we wanted to do was just sample the parts of the light that we know we were going to hit, one for each light, and see if we're occluded, right? It highly biases our samples in favor of, areas where we know we're going to get signal. That doesn't happen here. We can't do that. So why would we want to even worry about this LE term in this way? Why do we care? Well, this emitted radiance allows us to have a surface that both emits light and also reflects light. So if you have something like lava, if you want to model, some sort of surface like that, or headlights on a car, which the surfaces of the headlights can both emit and receive light, reflected, that sort of thing. You can use this LE term to have a surface that itself emits light. So it's not really using this direct lighting idea, which kind of just injects itself into the middle of the rendering equation, right? Sort of this like other thing that injects itself into the rendering equation. Instead, it acts as a surface like everything else, but it has an emission term. So again, we don't have any surfaces. We don't give you anything that any models that actually have emitted radiance in Scotty 3D in any of the examples. However, it's just important to know that's kind of what we're talking about here. And also, it's technically possible to support this in Scotty 3D. You can. There is an emissive material. Okay, so one last thing I want to talk about in terms of like the rendering equation itself, before we get into some Scotty 3D specific stuff, is this idea of managing cosines, right? So there are two cosines really that there are lots of cosines that you run into in this assignment, and you need to make sure you have your cosines straight. And actually, when I was preparing this lecture, I posted it in the Slack, and I actually got these flipped personally. Like it actually happened to me just like literally an hour and a half ago. So really need to be careful about this. This particular cosine has to do with the solid angle projection onto basically the amount of light that goes through a one steradian, basically, right? It's the solid angle projection onto a point. And some people had mentioned in the on the page for the slides. Well, okay, so this is saying, well, first of all, we have this idea of radiance, which is the projection. So like the whole idea is that we're projecting this circle on the edge of the hemisphere onto the plane, and then that reduces the area by a term cosine theta, where theta is the angle to the normal. And then this is saying here that this term is reliant on the parameterization of a sphere, but this term is it seems like Lambert's law is the same thing, right? So like as the rays of light are at a more oblique angle to the surface, right? It gets the radiance goes down by a factor of, or not the radiance, but the amount of shading onto this area goes down by a factor of cosine theta. And it's very natural to think like, wait, aren't these the same thing, right? This is a tilted thing being projected onto a plane. This is a tilted thing being projected, right? Aren't these the same thing, right? Isn't this cosine due to Lambert's law? But no, you have to remember that what's really going on here is these are solid angles, right? We are not talking about areas here. We're talking about solid angles. So really this visualization here, don't be fooled. We're really talking in the limit as this hemisphere goes to, it becomes infinitesimally small. So that is why, and really this is just a general property of the steradian, right? As we come in a more and more oblique angle, right? The solid angle incidence of some energy is going to be dependent on cosine theta. I have a link here that goes a little bit more into steradians and solid angles if you'd like to learn a little bit more about this. But sort of, it doesn't really matter too much in terms of implementing this assignment or anything. But just for your own understanding, this cosine is not, in fact, due to Lambert's law. It's simply due to the parameterization of a sphere and how we're thinking about solid angles. And basically, no matter however you parameterize steradians, right? However you parameterize the hemisphere, this cosine term is always going to show up. So it's somewhat intrinsic to solid angle energies. But it is not Lambert's law. And just the fact that they both happen to include a cosine term is invariant to what is actually going on here. Okay. So next thing I want to talk about, this is getting a little bit closer to, actually looking at the code. We're getting there, trust me. Is this notion of a delta BRDF. All right, so I have the rendering equation written up here. So for a mirror, right, like consider a mirror as one of the BRDFs you have to implement. Here's one way you could write the BRDF, right? So we have two vectors, WI and WO, right, just as always. And, we talked about in the lecture, we need to divide by cosine theta I, where theta I is the angle between WI and the normal, right? If, and this is equal to theta O, by the way, right, just by definition of the reflection function. If omega O is the reflection of omega I, right? So, or WI, WO. So, and then 0 otherwise, right? So we just have this, we kind of have this piecewise function that's, a positive value for exactly one value of WI and WO and 0 for everything else. Okay. Well, if you kind of think about it, this was mentioned in lecture, but think about this like very critically, right? Think about all this stuff we've been talking about with Monte Carlo integration, sampling. How do you even sample this, right? So yeah, oh yeah, by the way, so the reason why we can, the way it was written in lecture is it uses this thing called a Dirac delta function. This is how Keenan wrote this BRDF in lecture. And so we have this Dirac delta function. So the Dirac delta is defined to be 1 for input value 0 and 0 for any other input value. So the Dirac delta function, named after mathematician Dirac. So we have 0, 1, and then everything else. And the Dirac delta function, just to be super clear, I'm going to write 0 here and 1 here. So it's 0, 0, 0, 0, 0, 0, 0. Okay, this is an open circle, meaning, it's not this value. And then it's 1. Oh my gosh, I got this wrong. Okay. Yeah, so it has to be 0. So at value 0, it is 1. And at value everything else, it is 0. Okay, so that's a Dirac delta function. You see this all over the place. In this case, what it's saying is when cosine of theta I equals cosine of theta O, then this will be 0, right? The inner expression will be 0. The Dirac delta function will equal to 1. So this is equivalent to what I've written over here. And then it's 0 otherwise, right? So, okay, so theta I and theta O are the angles between, in this formulation, between WI, WI in the normal and WO in the normal. Right, so we have some surface here, we have a point of intersection, we have our reflection here, and then we have our normal. Okay, right, so I guess more concretely we would write this, both of them going out like this. So if WO, if this angle here these angles are the same, therefore the cosines are going to be the same, then we know that this then this is going to be equal to 1 over cosine theta. Otherwise, it's going to be 0. Okay, I think I've repeated that enough. So yeah, back to my original question, like how do we actually sample that? And if you think about it, right, like, you know, our sampler is just picking uniformly random directions off the hemisphere, right? I showed you the bit of code before that actually does that. And this would mean it would need to exactly guess many times the incoming vector, right, wi, up to floating point precision, right? So like that's like impossible. That would never happen. You need countless samples. You need to be running your path tracer for years, for years to actually integrate to something, right? On any of these delta BRDFs, any BRDF with a delta function, with a direct delta function involved. So like, how do we reconcile that? How do we get around it? Well, like, I mean, you know, in this case, there's only one vector, right? So why are we sampling uniformly all possible directions? We know we could just bias it completely in the one direction that we actually care about, right? A mirror is only ever going to reflect light in one direction. So, you know, we can just step back and say, well, let's just reflect it in that direction, right? And then change the probability distribution to just, you know, the probability distribution of our sampler to be just 1 in that direction, right? So now, broadly, you know, I've characterized these delta BRDFs as having exactly one possible value that is non-zero. But in general, in Scotty 3D, we define these delta BRDFs to have, it's basically any, you know, finite number of points. So, you know, in particular, we are also going to call the glass material a delta BRDF because the glass material has basically 2 possible states. If you have a Fresnel reflection, it'll reflect across the normal, right, if you're at a grazing angle. And alternatively, if you kind of hit it straight on, you'll get some refraction, right? So you kind of have 2 possibilities at each point P, depending on the angle of incidence, right? So here's the same point P, and in this case, it's actually going to reflect, and then in this case here, it's going to refract. So there's 2 possibilities. We still call it a delta function for the same reason, right? It's just any situation where we pretty much only have 1 or 2 possibilities, right, that we couldn't possibly hope to sample. So we call that a delta BRDF. And so one important thing to keep in mind is that these delta BRDFs don't use direct lighting. And if you kind of think about it, like, they don't really need to. I mean, theoretically, like, if we were going to be very exact, we would include the direct lighting term. However, you know, if you kind of think about it, it's pretty unlikely that you're actually going to hit the light by one of these delta BRDFs. So what we basically assume is that for all of these delta BRDFs, that all of the light is coming in indirectly. So you're going to need at least 1 ray bounce before you're going to be able to see these surfaces. So that's just an assumption we make in Scotty 3D. You're welcome to make it. If you really want to, you can also change the delta BRDF to use direct lighting, but it's not really going to affect your result all that much. Okay. So, oh my gosh, we're looking at code now. So here is a bit of code that you've seen before. This is task 4. So let's talk a little bit about, again, let's just go through, you know, this code was given to you. This obviously doesn't include the answer to task 4. But let's just go through the application of the rendering equation in the direct lighting part of Scotty 3D. So, first thing to point out is it's explicitly, in the direct lighting portion, it's actually checking if the BSDF, right, the BRDF is a delta function, right? So it's not if it's a delta function, we're not even going to start doing direct lighting. So first thing to notice, okay, so it's iterating through all of the lights, and then there's a certain number of samples that we need for each light. That this all has to do with the command line options. By the way, there's also this notion of a delta light, which is something like a point light, or where there's really only one direction to really go in which case it's only going to do one sample. But I wouldn't worry too much about that. It's just another idea of using a direct delta function to define a light. But for now, just say, okay, we have some number of light samples. So what this function does here, this call, is it actually samples a random point on the light. So imagining we have an area light, it's going to pick a random point on the area light. It's going to give you a vector that is the direction to the light, and it also gives you the distance to the light. And it gives them to you in these sort of output variables. And then it also gives you the probability that it gives you the probability of randomly selecting this random sample point on the light source. And it's going to weight the output radiance according to the function that we were talking about, that I showed you, that slide from Keenan that Keenan was showing, for normalizing the actual output radiance by the solid angle. So that's included here. So this is already done for you, right? Like all of these sampling functions, if you look at the file light.cpp, these are already there for you. So you already have these. So you don't have to worry too much about, the specifics of this. But it's important to know that it's there, because that's actually how everything is working. It's how anything gets lit at all. Another thing to note is that we need to account for the probability, right? So this is that PR variable. We need to account for the probability of hitting this patch of the area light, right? Because if we don't do that, it's going to bias our sampling, right? We're going to get a higher radiance in areas that are higher probability. And if you think about it, right, what does this remind you of? We're accounting for a change in probability, right? So our sampler has sort of a biased probability in some direction, right, on account of this whole projection onto the hemisphere, and we're dividing by it for some reason. Well, that should remind you of that law of the unconscious statistician, right? So we have our function f of x, which is a very complex function in this case that involves, it's the rendering equation, right? So it involves the sampling of this point on the light, and if we were to just integrate, right? If we were just to find the expected value of f of x, it's going to depend on the probability distribution of x, namely, the probability distribution of all of these potential vectors on the light. So we need to normalize by this probability. So what we're doing is we're including the reciprocal of p of x in f of x. That's why we're dividing by the probability. So that's why we're doing this. Like a lot of people are it's kind of intuitively like nice to think about, like, it's like, oh yeah, I divide by the probability to, normalize it somehow. But keep in mind this law here. It's a very simple thing, but it's very important. And that's what we're doing here, where what we want is we want to recover the actual expected value of the unbiased f of x, where all of these are uniform, right? So this is it, where this is a uniform probability. But in order to do that, we need to normalize by the sort of biased probabilities. So we're dividing, we're sort of putting a, over px x term in here so that these guys cancel out, right? And then we're left with just sort of the an unbiased, right, like integrated probability. Sort of broadly, that's what we're doing. Okay, so now we have a few more terms in here I haven't mentioned. So we have the actual radiance of the light, right? So that's just that's defined in the 3D model file or whatever. We have the BSDF of the surface, which is also going to that has to play into things, right? Like how much the surface itself reflects light. We have our cosine theta term, which is from the considering it's the parameterization of radiance. And okay, sorry, have another second on the slide. So there we have it. So it's important, to understand where all this stuff is coming from, right? Because if you don't, then when you're running into issues later in the assignment, and you're just like looking at your scene and it doesn't work, you need to understand where all of these terms come from. Right? As I mentioned in the very beginning, the bugs that you'll run into in this assignment are math bugs. They are physics bugs, really. They are not really generally like algorithms bugs that you might be used to in a computer science course. Okay. So, all right, now let's get really into like the details here. This goes back to Mark's excellent question. Actually, I don't think I talked about this quite yet. But okay, so yeah, there are actually two functions. Yeah, okay, so this is something else. There are actually two functions you need to implement for each BRDF. So there's this one function. So here's the diffuse BSDF that you're given this code. I'm not giving you the answer by showing you 1 over pi. I think we talked about that in lecture. Oh yeah, about sidebar. I've had the normalization term for diffuse BSDF twice in computer graphics interview questions. So maybe you might want to keep that in the back of your mind if you're interested in that kind of thing. It's a good thing to know off the top of your head. So anyway, so the function f, right? So we have as inputs, we have the ray direction. So this is sort of like your classical BRDF representation, right? So we have some uniformly sampled or somehow sampled, maybe cosine weighted sampled input and output direction. And we have sort of, all we need to do is we just need to return the radiance given those input ray directions. And notably, right, we can see here, it's called during direct lighting, right? So that's what's called right here. Right, so this is what is called during the direct lighting portion. This function f. So we're not generating any samples out of the surface in this step. Come on. Okay. So yeah, f is called only during direct lighting. Only. Okay, so a consequence of that, recall that direct lighting is never evaluated on delta surfaces, right? So namely mirrors and glass. For mirrors and glass, f is never called, ever. You can put a print statement in there, put in assert false in there. It will never get called. You can use it for your own convenience, right? Like it makes sense to, for example, call f with the result of sample f, which I'm going to talk about in a second. But just for your own reference, f is only called in the diffuse BSDF because that's the only one that you have to implement that is not a delta surface. Okay, I just realized this should say sample f. Okay, sample f. Okay, so sample f. So for this one, we only are given as input the outgoing ray direction WO, right? So again, this was we're talking about the direction sort of towards the camera in the path, right? And what we're trying to do here is generate a random sample WI, right, going out. So again, we're kind of looking for, we're trying to shoot a ray out so that it finds a light. So that would be the incoming ray direction. So we need to use, this is actually an output variable. Notice there's no const. And we also need to provide the probability that we actually choose that particular vector, right? That particular WI. Okay, so step 1, generate a sample WI. Step 2, find that sample's PDF. Step 3, we need to, then step 3, we return basically the same thing as F, right? So given that WO that we were given and the WI that we just generated, give an output the actual radiance. Okay, now when is sample F called? This is called by the code you will write in task 5. So in task 5, you're going to be calling sample F. And that's the whole idea, right? It's like you hit some surface, right? Some diffuse surface, right? Some non-delta function surface. And you need to generate, or actually, I don't want to say non-delta function, just any surface, right? So even the mirror, you're going to be calling sample F. Even the glass, you're going to be calling sample F. So you hit any surface, and the goal is to see what direction you go to next, right? You need to sample a new direction to go. But you also need to make sure that you are not, that you're still generating the correct result, right? So if that sample is biased in some way, right, you need to divide by the correct PDF, right? So just like we had to divide by the probability in direct lighting, you need to divide by the probability in indirect lighting. So, okay, so yeah, this goes directly to Mark's question from earlier. So, common point of confusion, WO and WI, omega O, omega I, both point away from the intersection point P. So that means that, and then also the outward normal, right? So let's say, I think I might have a figure for this, but the outward normal, so like the normal of the surface, is defined to be the positive z-axis. Okay, so additionally, in the case of refraction, right, so you're going to be implementing refraction, the z-coordinate will be negative, right? So you can know if a ray is coming into a surface if the z-coordinate is positive, and you'll know that it's like it started inside of a surface if the z-coordinate is negative, right? And that might sound confusing at first, but it makes sense if you look at this all from the perspective of, okay, I have this surface here, here's the outward normal, right? And then let's say I have another ray that's coming in from inside of this sphere, right? So if we think about it in terms of like, oh, well, okay, so all of these rays have an origin at P, right? Then really we don't have an arrow going this way, we have an arrow going this way. Okay? And so, yeah, okay, that makes sense, right? So Z should be negative, right? Because this is the positive Z axis here, this green line. Okay, yeah. So whereas if we had another ray, okay, maybe this blue ray that's coming in this way, then it would be pointing out here, and then it would have a positive Z coordinate. Okay, so the upshot of all this is for the case of refraction, where we can start inside of a sphere or some object, the Z coordinate will be negative when, excuse me, exactly when we start from the inside of the object. So that is actually particularly important when we're talking about Snell's law. Okay, so how did this actually happen? Like, how did this coordinate transformation happen? Maybe if you if things make a little bit more sense to you, if you can actually look at the code, it has to do with this O2W matrix and W2O matrix, right? So O2W is a matrix that is a rotation matrix that converts from world space to object space. And W2O is a matrix, or sorry, it's the other way around. O2W converts from object space to world space, right? So from the space of the intersection, the space that I've just defined, to world space. And then W2O is a rotation matrix that does the opposite, right? It converts from world space, direction vectors in world space, to direction vectors in object space. Object space being this thing where z is equal to the normal, and so on. So one last thing I want to, kind of mention here is that the dot product of any of these vectors with the normal is just the z coordinate, right? So, maybe you might write like dot product of the normal and WO if you really want to. But really, if you want to have the dot product of some, because it's very common, right? You want this angle theta. So let's say this is like some alpha. So then we know that theta is equal to, cosine theta, right? Because you'll need this, obviously. Cosine thetas are all over the place. Cosine theta is equal to alpha dot, the normal, which is equal to alpha dot z, right? This is the dot product. This is just a, accessor. Okay. Okay, so we're really in the home stretch here. So some just general hints and tips. First, for the diffuse BRDF, really think carefully about the PDF value. People get this wrong, and it shouldn't be that hard, right? So you have, you're either going to be sampling uniformly, which is the implementation we give you, or I highly recommend trying this, implementing a cosine-weighted sampler, which we give you some notes for it. It's optional, but we give you notes for it. And after today, after looking at how the derivation of the uniform sampler, you really should be super well set up to implement the cosine-weighted sampler as well. And also remember to use the diffuse BSDF albedo variable. Some people neglect to use that, even though we actually use it in the function we provide to you, which is pretty crazy. The mirror BRDF, the only thing I really have to say is it's pretty straightforward. You keep your coordinate base in check. Don't accidentally flip your normal or something. But remember to use the mirror BSDF reflectance variable. So the radiance that you're returning should include this reflectance variable as a term. And then finally, for the glass, this is easily the most complicated out of the three. You should be using somewhere in your sample F function, it should return some multiple of glass BSDF reflectance and glass BSDF transmittance. Common error, just a hint, the PDF is not 1. And finally, so there are some really good notes in on the wiki for implementing the Fresnel term, right, which we talked about in lecture. There's one formulation we give in the wiki, and it says it in like one line on the wiki. I really highly recommend using Schlick's approximation for computing the Fresnel term. One, it is much easier for you to actually implement. There are far fewer ways for you to actually go wrong in implementing it. So that's one reason. 2, we actually use Schlick's approximation in our reference solution. And 3, it is far more robust. And what I mean by that is there are fewer opportunities for things like dividing by a very small number. There are just fewer divisions in general. It's a simpler expression, and it tends to lead to fewer numerical issues, right? Meaning issues where numbers go to infinity because of a small division is really the canonical example, but also things like floating point error propagating, weirdness like that. I, again, highly recommend using Schlick's approximation just look up the Wikipedia article on Schlick's approximation. I think that's what we actually linked to on the wiki. Really, that's the way to go for computing this term FR. Okay, another note on grading. So specifically for task 6, I'm going to be grading task 6. So I'm actually going to run your code remotely on the Andrew Unix cluster to render the Cornell box, right? So cvspheres.dae with your pathtracer at these pretty demanding settings. So that means it's 8 threads, 4 light bounces, 1024 samples per pixel, and 800 by 600 resolution. So a lot of students just never try a render that's this that is this demanding. Maybe for lack of time, or they just don't really feel like it, or they didn't really think that it would behave differently on a high sample rate. But I highly recommend that you really try this, because you could have a performance regression when you have a lot of samples, right? So for example, if you have some part of your running time depends on the number of rays that are sent out, you know, if you have some expensive calculation that's happening for each ray, this will totally chug and it'll look really bad and you won't hit this 30-minute mark. Now 30 minutes is very, very, very lenient. Our reference takes less than 15. And our reference isn't exactly optimally written. It's kind of poorly written as well. I shouldn't say as well, it's kind of a roast. It's pretty poorly written. It has a lot of technical debt in our personal implementation. So you can do better than even our implementation. So yeah, so if you can't hit 30 minutes, it's likely that you weren't going to hit, 30 days. It's likely that there was some sort of serious issue, performance issue in your implementation. Now also there can be correctness issues with a sample rate this high. So I realize I'm over time, so I'll finish up quickly. So yeah, upshot, test your code. And also, now if you don't apply this, it's fine. If you don't try these changes, I'm going to apply them myself manually. But I highly recommend that you integrate changes to the base code that allow you to remotely render via SSH. So there's a guide for this on Piazza that I recommend you check out. I don't have time to show you how to install it because, again, I'm low on time. But if you ask on Piazza if you have any issues, let me know. So this will allow you to remote into the Andrew Unix cluster and render remotely. So it should be pretty manageable for you to run these like sort of half-hour renders. So now I want to just give some suggestions for improving performance. The biggest one really is to use a profiler. Right? We talked about this in the Intro to C++ lecture, but really this is the fastest way to solve performance problems if you realize you have one. Because most things have to do with something silly, like not passing by reference, most serious performance issues. And if it's a little bit more non-trivial, a profile will really help you pin down what is going wrong. Really an essential tool for any C++ programmer. Generally, avoid using trig functions. You can get by for almost everything you'll need to do, all the math you'll need to do, almost all of it, except for some things like that one arc cosine in the uniform sampler. You can get away with dot and cross products almost all the time. Remember that the dot product has magnitude, or the dot product is dot product of AB equals magnitude of A times magnitude of B times cosine the angle. Right? So you can use that. And the cross product, the magnitude of the cross product is the magnitude of A times the magnitude of B times sine theta. Right? So you can use the dot and cross products to recover cosine and sine. Just like, remember, when you needed to compute cotangent earlier, I believe. You needed to compute cotangent at one point. Maybe that's assignment 4. I forget. But yeah, you could use dot and cross product for sine and cosine. Avoid very recursive code. So a very common piece of very recursive code that people tend to have is a BVH traversal from task 3. So I recommend you convert this to a sequential algorithm. You can do this with just a stack. That'll really help speed up your code. Keep in mind, there are millions potentially of arrays that are traversing your scene. And for each of those arrays, if you're doing like a 20 recursive function, it's really going to slow down your performance. So converting to a sequential algorithm is really actually going to have a surprising amount of help. And you'll probably find if you have a recursive algorithm that if you go into a profiler, your BVH traversal is taking up a large chunk of the time. So next up, there are some helper functions at the top of bsdf.h. They do things like compute the sine and cosine between various angles. So I recommend you, for example, sine of, WO with the normal and stuff like that. So definitely use those. That makes it even easier to avoid having to do trig functions by yourself. And again, remember, there are millions of arrays, especially in this render that I showed, these settings I showed on the last slide. So really make sure your code is as fast as possible with respect to each raycast. Okay, so finally, it's like last slide, some suggestions to improve correctness. So first of all, this is like a really, really common mistake. Just don't ever clamp radiances, right? So don't clamp a spectrum, ever. Just don't do it. Your answer will be wrong. There is always an underlying issue that this clamping is supposed to be a Band-Aid fix for, whenever I see it. So one common source of this is sometimes students will see like these white speckles in their renders. So just like noise can sometimes manifest as dark spots on your render, it can actually also manifest as white spots if you're sort of like extra lucky. So the first thing I would suggest if you see these little speckles is instead of clamping the spectrum somehow, try turning up the sample rate. So if that doesn't fix it, you probably have some sort of math error. So keep in mind also that a spectrum can have color values that are greater than 1. So, especially because like lights, for example, can have color values greater than 1, with the norm greater than 1. So, yeah, it's really important that you don't clamp spectrums ever. Another thing, make sure your PDF integrates to 1, right? So like for all your BRDFs, you're going to be coming up with this PDF. Make sure that over the hemisphere, it integrates to 1. Otherwise, what that means is, right, you're dividing by the PDF, right? And then that's integrated over the hemisphere. So that means that your rays are actually going to gain energy, right, or lose energy. But if they integrate to something less than 1, then they'll gain energy. And you'll get something like this picture on, at the end of the day, right? Because, this person happened to have their PDF be too small, and then you'll get this like white noisy mess. And you may not even see it until you have many samples per pixel, which is a little scary, right? Because you'll need to gain enough energy for it to kind of really blow out like that. Also, keep track of your cosines. We mentioned this a few times that cosines come from a few different places throughout this assignment, right? Cosine theta on the normal. And, it's actually pretty funny because at this point I can kind of look at a result and tell what the bug is before I even look at your code because, if, for example, in this case, this student clearly missed a cosine because we can see that the edges of this sphere are dark. So this means that the student missed a divide by cosine somewhere. Of course, I'm going to look at your code when I'm reviewing. So I'm going to be the one who's reviewing the BRDFs. And I'm going to look at your code, right, to make sure that you got the term. So if it was some crazy other thing, I won't take off, too many points or anything. So don't stress about it. But make sure that all of the terms that you do need to include, you include. And so lastly, just last piece of sage advice, banging your head against code in this assignment, which may have worked in other assignments in this class and just generally in CS, it really won't work in this assignment. If you're really getting stuck, what I would recommend doing is moving to pen and paper, right? Coming to office hours, posting on Piazza, trying to make sure that your understanding of the underlying math and physics, the radiometry, is correct. Because that's really the best way for you to actually ensure correctness in this assignment. Okay, so sorry for keeping you guys an extra 9 minutes. That's all I have to say about assignment 2. Does anyone have any further questions? A lot of content. Wait like a minute for someone to type something, if they will.
Actually, I had a question.
Yeah.
I still didn't fully understand the biasing concept. We divide when biasing.
Yeah. So, okay. So yeah, that's a good question. Okay. So I'm gonna return to the slide on the where was it? Oh yeah, under Monte Carlo. So when we were computing pi, law of unconscious statistician. So the general idea here is we have this sort of integral that we're doing, right? And so the general idea of the law of unconscious statistician is that so we're trying to compute the expected value of some function, right? Our function f in this case is the radiance, right? So like L out, right? That's what we're trying to compute here. So we're trying to compute, right, the expected value of L out, right? And we are, in order to do that, we need to sample L out, right? We have this term in L out, right? L out takes in an outgoing ray direction, right? That's our x, the outgoing ray direction, and is sampling, or actually, sorry, x here is the random variable. So we're given our outgoing ray direction, yes, and we're sampling over many incoming ray directions. So this is omega in, right? And so sort of kind of hidden here as a non-like parameter, right? So like you can kind of just consider it part of f is kind of in here is omega out. So the way, at least looking at it through the lens of law of unconscious statistician, is that inside of this term f of x, right? Or sorry, not inside of this term f of x, like W in has a distribution, right? And that's dependent on the BRDF of the surface, right? The things that we're sampling over have a distribution. So if we didn't do anything, if we didn't multiply by anything or divide by anything, right? What would end up happening is if we tried to find the expected value via the normal way, right, using law of large numbers, what we would end up integrating is we would have this term for the probability that we sampled x. Does that make sense? Like if we didn't normalize by anything, this term would be here.
Okay.
So, another way to think about it is, okay, what can we control? We can control f, right? We can change f. We can change the function f. So what we're doing is we're adding in a term 1 over px x into f, right? So, we can say like this is f prime of x time, we're saying this is 1 over pxx of f of x, right? The original, right? And that's to account for the probability distribution of our W-ins.
Okay, so basically L out should be uniformly, we want it to be uniformly distributed but because the incoming rays are not uniformly distributed, we have to use this.
Yeah.
Okay, okay, I
Yeah.
see.
Yeah,
Okay.
exactly. And yeah, so and then also even if they were uniformly distributed, um, for example, in the case of um, in the case of like a diffuse surface, the probability distribution is still uniform,
Okay.
but it's not equal to 1 either. It's equal to something else, which I don't want to give away because that's for you guys to figure out. But um, that would change this result. It would make the whole scene darker.
Okay.
Right? So we still need to account for it, even if it's uniform. So the point is that we need to worry about this, right? We need to account for the this property of this inherent property in sampling uh, integrals, right? In finding expected values by the law of large numbers.
Okay.
Yeah.
That makes sense. Okay. All right. Thank you.
All right. Any other questions? Last call. All right. So yeah, I'll continue taking questions, online on Piazza or whatever. Thank you guys all so much for staying. The few of you that stayed. Oh yeah, you're welcome, guys. And okay, good luck on the assignment. And I look forward to seeing your beautiful renders.